Carbon Capture Utilization and Storage. Rolling the Energy Transition. Offered by Group 9. Get in there and enjoy the show.
Hello everyone, and welcome to the seminar about carbon capture, utilization and storage and its role in the energy transition. Carbon capture, utilization and storage refers to a suite of technologies that involves the capture of CO2 from launch point sources, including power generation or industrial facilities that use either fossil fuels or biomass, or capturing CO2 directly from the atmosphere, if not being used on-site. In fact, the captured CO2 is compressed and transported by pipeline, ships, rail or trucks, to be used in a range of applications or injecting into deep geological formation for permanent storage. Today there are 21 CCUS facilities around the world, with a capacity to capture up to 40 megatons of CO2 each year. If all of the new projects announced since 2017 were to proceed, the amount of global CO2 capture capacity would more than triple. Today, CCUS is an early stage of commercialization. Thus, measures targeted at specific applications are required to build a business. CCUS may not be a new technology or a new concept, but it has been the subject of global interest and attention in recent years. Let's move now to the technological part. There are three possible strategies that can be applied in combination with coal, natural gas, or biomass as primary energy source. The pre-combustion deals with the removal of carbon from fuel before it is used. The post-combustion deals with the removal of CO2 from a specific stream of gas, typically exhaust gases or generic CO2-rich stream, while oxy-fuel involves the combustion of a fuel using nearly pure oxygen. These strategies are usable by electric generation, hydrogen production, or industrial processes. Let's now move to the main technologies. Chemical absorption of CO2 is a common process based on the reaction between CO2 and a chemical solvent. This operation is usually performed using two columns, one for the absorption and one for the regeneration of the solvent, as we can see from the picture on the right. Chemical absorption using a amine-based solvent is the most advanced CO2 separation technique, requiring high capital cost and high heat power. Physical separation of CO2 is based on either adsorption or absorption. Physical adsorption makes use of a solid surface, while physical absorption makes use of a liquid solvent. The current use is main natural gas processing, ethanol, methanol, and hydrogen production. Let's move now to the early stage technologies. So, oxy-fuel involves the combustion of a fuel using nearly pure oxygen. Because of the flue gases is composed almost exclusively by CO2 and water vapor, the latter can be removed easily by means of dehydration to obtain a high purity CO2 stream. The option requires high consumption for oxygen separation and high capital cost for the new combustor, but leads to huge capture efficiency. Potential applications are oxy-fuel gas turbine, coal power plants, or cement industry. Let's move now to the calcium looping that involves the capture of CO2 using two main reactors. In the first reactor, lime is used as a sorbent to capture CO2 from a gas stream to form calcium carbonate. The calcium carbonate is then regenerated, resulting in lime again and a pure stream of CO2, which is then stored. The installation of the calcium looping inevitably involves the increase of investment costs, but this is limited by the removal of the desulfurization unit, while the levelized cost of electricity of the plant value is strictly dependent on the possible carbon tax. Let's move now to the membrane separation that is based on polymeric or inorganic devices with high CO2 selectivity, which let CO2 pass through but act as a barrier to the other species in the gas stream. Membranes for CO2 removal from syngas and biogas are already commercially available, while membranes for flue gas treatment are currently under development. Chemical looping, instead, is a two-reactor technology. In the first reactor, in fact, small metals are used to bind oxygen from the air to form a metal oxide, which is then transported to the second reactor where it reacts with fuel, producing energy at a concentrated stream of CO2. This technology represents a valid alternative in terms of low energy penalty and costs. Let's move now to the negative emissions technologies. PECCS involves the capture and permanent storage of CO2 from processes where biomass is converted to energy or used to produce materials. In principle, if some or all the CO2 released during the combustion is captured and stored permanently, the process is carbon negative. But in practice, a life cycle assessment is needed to identify if negative emissions are reached or not. The most advanced BECCS projects for capture of CO2 are from ethanol production, biomass-based power generation, while industrial applications are only at prototype level. while DAC technology extracts CO2 directly from the atmosphere for permanent storage or for use. To capture the CO2 from the air, these rely either liquid or solid solvents. The AC will most likely always need a source of heat, such as natural gas, but with advantage of a high flexibility in siting. The main drawback of this technology is the low CO2 concentration in ambient air, which makes this technology high energy intensive and expensive. Most of the existing plants are small-scale pilot plants. In this slide, we can see a cumulative representation of the readiness among different sectors. As we can see, the capture of CO2 from ammonia production, natural gas processing, production of fertilizer, and long-distance pipeline for EOR have reached mature stage level. While for industrial processes and power generation that affect more than 70% of global emissions, CCS remains at its early stage level. In the Sustainable Development scenario, nearly two-thirds of the cumulative emission reduction from CCUS to 2070 come from the technologies that are currently at prototype or demonstration stage. The other one-third comes from technologies that are already mature, and this can be scaled up rapidly. In 2030, such technology in power and fuel transformation will contribute around half of the cumulative emission savings. Major improvements to a wide range of technologies that are at prototype or demonstration stage today are needed. A pivotal role in the next decade can be played by chemical absorption for natural gas-fired power generation.
After CO2 has been captured, we have to find a way to deal with it. One of the solutions is to store it underground in depleted oil reservoirs. This process is known as geological sequestration and, according to recent estimates, it allows to store up to 1,000 gigatons of CO2. CO2 injection can also be exploited in reservoirs that are still producing oil. Fluid injection is used in reservoir engineering to maintain the reservoir pressure and boost the oil recovery. The first fluid to be injected is usually water. After that, an additional fluid with particular chemical properties can be injected to further enhance the production. Water injection is known as second recovery, while the injection of the subsequent fluid is known as third recovery. CO2 is miscible in oil and it is able to dissolve in oil and displace the oil from the pore space of the rocks, additionally enhancing the production. In the chart, you can appreciate how water and CO2 injection increase the oil recovery. However, CO2 injection is not a free lunch. An accurate economic evaluation must be performed to evaluate the economic feasibility of the process. The cost of this process can sharply vary, being a function of where the CO2 comes from and of the possible transportation system required if the CO2 source is far from the reservoir. For example, if the CO2 comes from another basin. CO2 is not going to be only stored. Many projects aim to use it in the future. The use of the previously captured carbon dioxide is a hot topic indeed. In fuel production, CO2 could be coupled with hydrogen to produce hydrocarbons through specific chemical reactions. CO2 use is a matter of interest also in chemical industry. The last example deals with the building materials, where CO2 is used in the formation process of materials such as concrete.
From an economic perspective, the development of CCUS presents some challenges: high capital investment, uncertainty surrounding long-term ownership, and public opposition to storage in some regions. The private sector is unlikely to invest in the technology unless it is obliged to do so, or unless it can make a profit from the sale of the CO2. Almost all CCUS projects operating today have benefited from some form of public support, largely in the form of capital grants. Some capture applications, such as natural gas processing, are mature and less expensive, requiring relatively limited policy intervention with respect to other applications such as heavy industry. As deployment increases, the market for CCUS should become more independent, requiring less government intervention. Targeted subsidies could be phased out, and the carbon pricing could become the primary measure to support investment. By now, Here are 4 priorities for governments to support a rapid scaling up of CCUS over the next decade. First, create the conditions for investment. Deploying CCUS on large scales require measures to make such investment commercially attractive. There are 3 key approaches. A. Place a value on reducing emissions, for example, with public programs that favor lower emission commodities or products, or tax credits associated with CO2 storage. B. Provide funding to support capital and operating costs for early projects. Grant funding programs can play an important role in supporting early CCUS deployment. However, they can be a heavy burden on public budgets, limiting their use to a small number of facilities. A rapid scale-up of CCUS will necessitate a shift towards market-based measures. C. Allocate risks across the public and private sector. For example, policy should consider the option to transfer the ownership of the stored CO2 back to governments after a specified period. The second type of policy is to target industrial hubs with shared CO2 infrastructure. This will make it feasible to capture CO2 at smaller industrial facilities, for which dedicated CCUS infrastructure may be uneconomic. CO2 infrastructure may be considered a natural monopoly, whereby high startup costs and economy of scale make it economically more efficient to have a single owner and operator rather than competing providers. The third kind is to identify and encourage the development of CO2 storage. Availability of safe and adequate CO2 storage is a prerequisite for investment. In many regions, however, significant further assessment work is required to convert theoretical storage capacity into well-understood storage. An atlas of CO2 storage resources should be developed. The last step is to boost technology innovation. In a sustainable development scenario, around 60% of the cumulative emissions production to 2070 hinge on technologies that are currently at the prototype or demonstration phase. Private sector participants in the innovation system greatly outnumber public sector employees, representing just 5 to 25% of R&D researchers in most member countries of the OECD. Risks of investment from being a first mover can sometimes be too high for a single country. Thus, international partnerships such as the Clean Energy Ministerial CCUS initiative and many other programs are providing an important foundation for collaboration on CCUS development and deployment.
Now we are going to talk about the CCUS role in the IEA Sustainable Development Scenario. Firstly, the Sustainable Development Scenario describes the broad evolution of the energy sector that would be required to reach the global net zero CO2 emission in 2070. In the IEA Sustainable Development Scenario, CCUS contributes nearly 15%. Let's now move to the role of the CCUS over time. The Sustainable Development Scenario evolves over the projection period with 3 distinct periods. In the first phase, to around 2030, the focus is on capturing emissions from existing power plants and factories. During the second phase, from 2030 to 2050, CCUS deployment expands in cement, steel, chemicals and hydrogen production sectors. In power generation, the focus is shifted to natural gas-fired plants. BECCS also expands significantly. In the last phase, from 2050 to 2070, the growth in CCUS application is due to BECCS, DAC and blue hydrogen production. In 2070, about 35% of all CO2 emissions captured are from bioenergy or DAC, most of which are stored, generating negative emissions which balance all the remaining emissions, so as to achieve a net zero emissions energy system. We now move on to the use of the captured CO2. More than 90% of all the CO2 captured in the Sustainable Development Scenario is stored, with 80% of the stored CO2 coming from fossil sources and industrial processes, and 20% from bioenergy and DAC. Only around 8% of total captured CO2 is used or recycled as a raw material in the production of fuels, chemical or building materials. Let's now see the policy instruments that may be implemented in the Sustainable Development Scenario. There is no one-size-fits-all policy template for CCUS. The appropriate choice or mix of instruments for each country depends on local market conditions and institutional factors. A range of policy instruments are at policymaker disposal to support the establishment of a market for CCUS and address the investment challenges. The measures include direct capital grants, operational subsidies, carbon pricing mechanism, demand-side measures, CCUS-specific market mechanism, regulatory requirements, risk mitigation measures, and continuous support for remuneration. Let's finally summarize the main aspect of CCUS technology. Positive aspects include possibility for reducing emission of existing fossil fuel power plants, reducing emission in sector where it's hard to abate them, low carbon blue and black hydrogen production and generation of negative emission applying CCUS as a DAC and coupled with biomass power plant. On the other hand, CCUS is affected by high capital cost, high cost of transportation and storage infrastructure, it reduces the efficiency of processes, and lastly, ad hoc policies are needed for technology development and deployment. In conclusion, CCUS can be seen both as a short-term solution to reduce existing emission in the energy transition period, and as a long-term solution needed to build a net zero energy sector, where CCUS is the only way to offset unabated emission from sectors where full decarbonization is not feasible. Thanks for your attention.